Hi, welcome to AP Calculus for East Aurora High School. Today in Chapter 2, Section 1, we're going to develop the limit definition of the derivative at a given point and practice using it on some examples. So you'll see that I've got a graph of a random function. This is just a generic function in front of us. We want to find a tangent line at any point P on the curve. So our first goal is to start and develop a point. So I'm going to identify a point on my curve, and again, I'm not going to identify it by coordinates. I'm just going to put a point here and call it the point P. Now the point P is going to have generic coefficients. Let's say that it exists at C, and if this is the graph of f of x, then the output would be f of c. I need a second point on my curve, so I'm going to identify this point over here as Q. Now you'll notice that to get from point P to point Q, I started right here at the x-coordinate of C, and I went over to an x-coordinate over here. I'm going to call that distance that I've gone from P to Q on the x-axis delta x. Delta x just means my change in x. Now you may be familiar with this from pre-calculus, and you may have called it h. In AP Calculus, you can use either one, the delta x or the h, and I will mention that quite often. Now Q, because it has been, it's a point that I've gone over delta x from C, that means that the x-coordinate at Q should be C plus delta x. So when I go to find the coordinates at Q, the input is going to be C plus delta x. The output is going to be f of c plus delta x. So we can then use those 2 points to find an equation of a line that connects the two. Now if you think about this, when I'm connecting 2 points on a curve, I hope that you remember that that is called the secant line to the curve. So in order to find the slope of that secant line, I'm going to use my slope formula. So remember that slope is just equal to the change in the y-coordinates divided by the change in the x-coordinates. Rise over run. So in order to do this slope of the secant line, and I'm even going to designate it as M with a little subscript of SEC standing for secant line, I'm going to go from Q back to P. So I'm going to say, let's take the difference in the y-coordinates. So the difference in the y-coordinates is going to be the y-coordinate at Q, f of c plus delta x, minus the y-coordinate at P, which is going to be f of c. That's my change in y, divided by the change in x. So the x-coordinate at Q is c plus delta x, minus the x-coordinate at P is c. So to simplify this, we have that the slope of the secant line is equal to f of c plus delta x minus f of c all over. I subtract the c's, and my denominator is just going to be delta x. Now, that's just a way of coming up with the slope of the secant line between the 2 points. My goal is to go ahead and find the tangent line. So to find the tangent line, that means that I've got to take my point Q and I've got to move it closer and closer to the point P. Well, in order to make the point Q move closer to the point P, that means that my x-coordinate at Q has to move closer to the x-coordinate at P. Well, in order to move them closer together, that means that this delta x has to get smaller and smaller. And as I make the point Q come closer and closer to the point P, I'm going to eventually get where Q is right on top of P. If Q is on top of P, then I really just have a line that goes through 1 point on my curve, and that's going to be a tangent line to the curve. So then let's change over to our definition for, instead of the slope of the secant line, we now want the slope of the tangent line. This brings about something that we learned, of course, in Chapter 1, our limits. We want to take the limit as delta x gets really, really small. That means we want to take the limit as delta x approaches 0 of that very same slope of the secant line, f of c plus delta x minus f of c all over delta x. Now again, you'll notice that I am specifically finding the slope of the tangent line at point P, and at point P I'm going to be given the coordinates c, f of c. I know back in pre-calculus you found the general form, but in calculus it's important for us actually to start with this derivative or slope of the tangent line at a particular point. So I have to be given a particular point. And that's what the focus of this video is. So here we have in this box, and you want to make sure that you write this clearly in your notes. This is the formula we're going to be using today. The limit definition of the derivative at a given point. What this really means is going to be our slope of the tangent line, the slope of the tangent line at the given point, c, f of c. Let's try our first example. The first example says let's find the slope of the graph of the curve f of x equals 4x plus 1 at the given point 1, 5. So we're going to use our limit definition of our derivative. So I'm going to start by writing that down, and I'm going to say the slope of the tangent line is going to be equal to the limit as delta x approaches 0 of f of c plus delta x minus f of c all over delta x. Now in this case we see that we are given the point 1, 5. So 1, 5 really stands for our c and our f of c. So this is 1, f of 1. So I'm going to plug that into my formula and say let's take the limit as delta x approaches 0 of f of 1 plus delta x minus f of 1 all over delta x. So our job is to evaluate this limit. So to evaluate the limit, we first of all have to write down what we are taking the limit of. When I want the function value at 1 plus delta x, what that really means is that I have to take 1 plus delta x and substitute it into my original function every place I see an x. So that tells me that I want f of 1 plus delta x, 4 times 1 plus delta x. I'm replacing the x in my function with 1 plus delta x. But don't forget about the plus 1 that's still in my function. So this right here stands for f of 1 plus delta x. Minus, well, f of 1, we know the output at 1 is 5. If I wasn't given that value, think about how you would find it. Remember that the input is 1, so to find the output, I can just use my function. Now let's go ahead and divide by delta x. And in order to take this limit, we of course first of all have to simplify our numerator. So I see that I'm going to distribute, and I'm going to get 4 plus 4 delta x plus 1 minus 5 all over delta x. Looking at the constants, 4 plus 1 minus 5 cancels. So right now I've got a 4 delta x divided by a delta x. And I'm treating this delta x as just a variable that stands together. But because I've got a delta x in both the numerator and the denominator, they will cancel. And the limit of the number 4 is just 4. So what this tells me is that the slope of the tangent line of f of x equals 4x plus 1 is 4. Now, some of you are probably realizing that we didn't even have to use calculus to find that. We know in this example that we have a linear function, so any linear function has a constant slope, and we always find that slope by the coefficient of the x. I was just trying to use a very simple example to use this formula first of all, but the rest of them are going to be a lot more complicated. Let's go ahead to example number 2, where we want to find the slope of the parabola. Our parabola is given the equation y equals x squared at the point P, which is 2, 4. Then, once I find that slope, I want to go ahead and find the equation of the tangent line, and I want to be able to check it on my graphing calculator. Now, I've given you a graph for this one, so you'll notice that I can actually find the point P right on my curve. So I see right here is the point P, and that's given the coordinates 2, 4. So I have to tell you in these examples what point I want you to use in order to find the slope of the tangent line. In the previous example, that slope didn't change no matter where I looked because the slope of a line is constant. But in the case of a parabola, the slope is going to change depending on what point I'm using in order to find that slope. So let's go ahead and use our limit definition. So we're going to say our slope of our tangent line is going to be equal to the limit. And it's really important that you keep that limit in here. Without a limit, we're not doing calculus. So the limit as delta x approaches 0. Now, looking carefully, I know that my c value is equal to 2, and my f of c, my f of 2 value, is equal to 4 in this case. So I'm going to use the formula f of c plus delta x, but in this case my c is 2. So I'm going to say f of 2 plus delta x minus f of 2 all over delta x. So let's go ahead and substitute our 2 plus delta x into our function where I see an x. Now you'll notice that my equation is y equals x squared. So I'm going to take the input, 2 plus delta x, and I'm going to substitute it for x, so that means I'm going to square it. There's nothing else in that function, so that's the extent of f of 2 plus delta x minus f of 2. Now when I substitute 2 into my function, I see that I do get 4, but I was also given the output for that ordered pair as well. All divided by delta x. So for this one, in order to find the slope of the tangent line, I'm going to have to simplify this numerator. If you have to go off to the side and say, okay, what is 2 plus delta x squared? By multiplying 2 plus delta x times 2 plus delta x, go ahead and do that. 2 times 2, of course, gives me 4. Outers gives me 2 delta x. Inners give me 2 delta x. And watch this last part. Delta x times delta x, again, thinking of delta x as just a quantity, a distance. That delta x, the whole thing has to be 4. So my numerator is going to be 4 plus 4 delta x plus delta x squared minus that number 4 that was also in my numerator, all divided by delta x. So I now have the limit as delta x approaches 0. Just going to order this off here. Of the 4's cancel, so now I've got 4 delta x plus delta x squared divided by delta x. Now each term in the numerator has a delta x, so I can divide everything by delta x. So I now have 4 plus delta x. Now when I take the limit as delta x approaches 0, that just means my delta x is getting so small that it's inconsequential. So this limit is equal to 4. Now what does that 4 represent? It is the slope of f of x at the point P, which in this case is 2, 4. And that's that makes sense in this problem. If I were to draw in that tangent line, I would say, yeah, that looks like that could have a slope of 4. Let's take the next step and now use that slope to find the equation of the tangent line. To find an equation of a tangent line, of course, we're going to use the point-slope formula of a line. So I have to have an ordered pair. My ordered pair is the point P, which of course is 2, 4. And I have to have the slope of the tangent line. We just calculated that slope using a limit to be equal to 4. So let's go ahead and make the equation of the tangent line. Y minus the y-coordinate of the point is equal to the slope times x minus the x-coordinate. Now technically in calculus you're allowed to leave it in this point-slope form, but I always go the next step and find the simplified slope-intercept form. So that's going to give me 4x minus 8 plus 4, so my slope, or my equation of my tangent line is y equals 4x minus 4. Now in the work that we're going to do with this in our textbook, the textbook then says, let's go ahead and take out our graphing calculator. Let's graph our original function y equals x squared. Let's graph this equation of our tangent line, y equals 4x minus 4. Make sure that this line is tangent to my curve at the point 2, 4. And that's a good way to check our answer for both our slope and for our equation of a tangent line. Now I'd like to look at a couple more complicated equations or functions. So our next function is going to be f of x equals 1 over x plus 1. Think to yourself, what kind of function is this? I've given you the graph of it. Do you recognize what it is? We'll be talking about this one in class. So we want to find the equation of this tangent line to the curve f of x equals 1 over x plus 1 at the point x equals 1. So here's my point x equals 1 right here. That's my P. Now you'll notice that P has an x-coordinate of 1. If I substitute 1 into my function, I get 1/2, and that makes sense according to my diagram as well. So let's go ahead and find the slope of the tangent line. Oops, sorry about that. I spelled that incorrectly. That's going to be equal to the limit as delta x approaches 0. Now this time our c value is 1, so I want f of 1 plus delta x minus f of 1 all over delta x. And again, in AP Calculus, it's really important that you understand how to use this constant value in our limit definition. I know we're going to be moving on to the general form with an x in there, but for this exercise we have to be able to do this with the constant value of 1. So we're going to say this limit of delta x approaches 0, we're going to substitute 1 plus delta x in for x. So I'm going to have a 1 over 1 plus delta x plus 1 minus my function value at 1, we already said was 1/2, all over delta x. Now before I simplify the complex fraction, I'm going to simplify my first denominator here. So this is going to be 1 over 2 plus delta x minus 1 over 2 all over delta x. Now to simplify this complex fraction, we're going to multiply the numerator and the denominator by the least common denominator. So in this case, we're going to multiply by a 2 and a 2 plus delta x. And don't forget to multiply both numerator and denominator by that. So you see that our practice with simplifying limits back in chapter 1 is really paying off here. So the slope of the tangent line will be equal to the limit as delta x approaches 0. Now when I take a look at that very first fraction and I multiply it by my least common denominator, the 2 plus delta x's are going to cancel, leaving me with just a 2 in that numerator so far. Minus the second fraction, the 2's will cancel, so I'm going to subtract the whole other factor, 2 plus delta x. And in my denominator, I'm going to have a delta x, I'm going to have a 2, and I'm going to have a 2 plus delta x. Now, don't be tempted to cancel off those 2 plus delta x's because I have to simplify my numerator first. So this is going to be the limit as delta x approaches 0. 2 minus 2 cancels, and then I've got a negative delta x left over, all over 2 delta x times 2 plus delta x. And again, make sure that you are clear on where all these factors are coming from. To solve this limit, I'm going to cancel off a delta x from the numerator and the denominator. So I see that in simplified form, this is going to be negative 1 over 2 times 2 plus delta x. Now it's time to take that limit, so the slope of the tangent line is going to be equal to, as delta x approaches 0, this slope is going to give me a negative 1/4. And again, if I look at this graph, I see that makes sense. If I draw in that tangent line at that point, it does look like, first of all, it definitely has a negative slope, and secondly, it looks like it very well could be negative 1/4. So always make that conscious check of your slope to make sure that it makes sense according to your picture. Now let's go ahead and make the equation of our tangent line. Again, in this case, the point that we're using is 1, 1/2, and the slope that we're using is negative 1/4. So my point slope formula says y minus 1/2 is equal to negative 1/4 times x minus 1. Take a second to simplify that and come back and check with my simplified answer. I have the equation of the tangent line y equals negative 1/4 x plus 3/4. And again, looking at my graph, that makes sense. It looks like the y-intercept of the tangent line could be 3/4 and the slope could be negative 1/4. Let's try one more example using this limit definition. For this example, we want to find the equation of the tangent line to the curve f of x is equal to the square root of x minus 2 at the point 6, 2. So I've already substituted my c value of 6 into my limit definition of the derivative at the given point. So this is going to be the limit as delta x approaches 0 of f of 6 plus delta x minus f of 6 all over delta x. Let's go ahead and substitute 6 plus delta x into my function. So when I do that, I now have the square root of 6 plus delta x minus 2 minus f of 6. And again, if I wasn't given the output, I could easily substitute 6 into the function and see that the output was going to be 2. All divided by delta x. Now, this, of course, is one where we're going to have to rationalize our numerator. So first of all, I'm going to simplify what's underneath the square root sign. So that's going to be a 4 plus delta x minus 2 all over delta x. Of course, I see that if I substitute 0 in for delta x, I am getting that indeterminate form. So that's why it's necessary to rationalize this numerator. So I'm going to multiply by 4 plus delta x plus 2 in the top and the bottom. And go ahead and do that. So I've got now the limit as delta x approaches 0. Radical 4 plus delta x times itself is just giving me 4 plus delta x. Outers and inners will cancel, so negative 2 times positive 2, negative 4, all over. And again, I never multiply this through because I'm looking for eventual cancellation. So delta x is going to be multiplied by the square root of 4 plus delta x plus 2. The 4's in the numerator cancel, so I'm going to go ahead and subtract those. And then I see that I have a delta x factor in the numerator that will cancel with the delta x factor in the denominator. So I now have the simplified form, the limit as delta x approaches 0, of 1 over the square root of 4 plus delta x plus 2. Substituting 0 in for delta x, I see that I'm getting 1 over the square root of 4 is 2 plus 2. So this slope of my tangent line is going to be equal to 1/4. And again, I could take a look at that on my calculator, look at the point specifically 6, 2, and see that the slope of the tangent line makes sense as a 1/4. Now, take a minute and find the equation of the tangent line and come back and check with mine. I got the equation of the tangent line to be equal to y equals 1/4 x plus 1/2. Now, please make sure that you've understood all of the examples that we've worked through today. If you have any questions, please come and see me during activity period. We're going to be working on lots more of examples like these in class. Have a great night, and we'll talk to you next time. Bye-bye.